Welcome to This Explainer. Today, we're diving straight into the true cost of black gold. Getting petroleum out of the ground. It's not just about digging a hole. It is a massive, literal battle against the crushing forces of nature. So let's head deep beneath the Earth's surface and see how this whole thing actually works.
Okay, let's dive right into this because I want to challenge what is probably the biggest misconception out there. When you picture an oil well, do you imagine workers drilling down into some massive, dark, hollow cave? Like this huge bubbling lake of oil where they just drop a bucket and pull it up? Well, geologically speaking, that kind of underground lake, it completely doesn't exist.
Right, so if you were to actually travel, say, 3 kilometers straight down into an oil deposit, you wouldn't find an open cavern or an underground river. No way. If you looked around, all you would see is rock. Hard, continuous, totally solid gray rock, just packed incredibly tight. So that myth of the giant underground lake, toss it out. The reality is that the oil is locked away inside what is essentially a solid rock sponge. To really wrap your head around this, you have to imagine taking a piece of that rock and sticking it under a powerful electron microscope. When you do that, you see billions of microscopic pores that are totally invisible to the naked eye. We call these capillary tubes, and they are so incredibly tiny that you'd literally need thousands of them just to hold a single drop of water. So the rock acts exactly like a giant kitchen sponge completely soaked in oil, just trapped under layers and layers of earth. But hold on, this isn't just a sponge sitting on your kitchen sink. It's buried under kilometers of heavy rock, which creates a crushingly intense environment. We're talking about pressure down here that's 300 times greater than our normal atmosphere on the surface. To put that into perspective, imagine a massive adult African elephant trying to balance its entire weight on a single postage stamp. Yeah, it's that intense. If you buried a car at this depth, the immense weight would instantly crush it down into a thin iron plate just a couple centimeters thick.
And honestly, the pressure is only half the battle. This is an insanely hostile environment. Temperatures down there easily exceed 100 degrees Celsius. I mean, if you introduced pure water into that environment, it would instantly boil and vaporize. Drop a plastic bottle down there, it melts into a puddle immediately. So it's in this terrifyingly extreme environment that engineers have to fight their literal war against the Earth just to extract this black gold.
So how does the process actually start? Well, mixed in with the oil inside all those tiny rock pores is a ton of natural gas. And because of the extreme pressure, this gas is dissolved right into the oil, exactly like the carbon dioxide dissolved inside a hot, shaken-up soda bottle. The second the heavy drill bit punctures that rock layer, the pressure at that specific spot drops instantly. That dissolved gas violently expands into bubbles, which forcibly push the stubborn oil ahead of it, looking for the only available exit, the narrow steel pipe. And boom! The oil shoots up the pipe with a massive roar, erupting right at the surface. Now, this initial phase, that's basically a free ride provided by nature. The Earth is literally pushing the oil out for us. But here's the catch, and it's a big one. It doesn't last. The natural gas escapes, the pressure in the rock sponge rapidly drops, and eventually, the well goes totally silent. Even when engineers attach those classic nodding donkey vacuum pumps you see in movies, they can really only retrieve about 10 to 15% of the total oil. Without extreme intervention, over 85% of that oil stays stubbornly locked underground in the dried-out rock pores.
So because that natural pressure just dies out, engineers have to drastically escalate the battle. They drill a secondary hole nearby, which they call a pressure well. Up on the surface, they hook up these absolutely massive, powerful water pumps. These machines run 24/7, pumping the equivalent of 20 full-sized city swimming pools of water deep underground every single day. What this does is create a massive underground hydraulic piston. The sheer force of all that water pushes through the rock pores, effectively squeezing and driving the remaining oil right toward the primary extraction well. Now, this water injection method is used all over the world, but eventually it creates a massive new headache, the 90% water problem. See, after a few years, water just does what water always does. It finds the path of least resistance. It washes out the widest channels in the rock, completely bypassing the oil. So before long, the extraction well starts violently pumping out this dirty mixture that's over 90% water, with only a tiny fraction of actual oil. And separating such a messy mixture back on the surface, it becomes incredibly expensive and incredibly inefficient.
So when water fails, engineers basically have to launch extreme chemical warfare. To scrape those absolute final drops from the microscopic sand grains, they'll start mixing thick, sticky polymers into the water. It makes it act almost like slow-moving wallpaper glue, forcing the oil out of those super tight spaces. If that doesn't do the trick, they'll pivot to injecting freezing liquid CO2, which chemically reacts with the oil, thinning it out so it easily slips up the pipe. And, as a literal last resort, they'll even inject superheated steam at 300 degrees Celsius to literally melt the heavy, stubbornly thick underground tar. It's wild. Now, what's really interesting about this next slide is the terrifying geological fallout of all this brute force. We really have to ask ourselves, what happens to the Earth when you forcibly remove millions of tons of liquid that's been supporting the crushing weight of the rock layers above it? To put it in perspective, the weight pressing down on these emptied rock sponges is roughly equal to 10 million fully loaded train cars. The Earth above doesn't just, magically float in place. The most dramatic example of this is the famous Ekofisk disaster over in the North Sea. Back in the 1970s, engineers built these massive steel and concrete platforms, calculating their height absolutely perfectly to clear the strongest winter storm waves. For 10 straight years, they pumped just astronomical amounts of oil out of the ground. But then, in 1984, sensors picked up something alarming. These billion-dollar platforms were slowly sinking into the ocean. By draining the subterranean rock sponge 3 kilometers below, the seabed itself collapsed under the weight. It basically shrank like a crushed cardboard box, dropping a staggering 4 meters. To save the structures from being completely swallowed by the sea, engineers had to pull off this high-stakes rescue, cutting the massive steel legs and using hundreds of synchronized hydraulic jacks to lift the entire platform 6 meters into the air. Just an unbelievable situation. And obviously, this geological devastation isn't just limited to the ocean floor. On land, the hidden cost shows up in a truly frightening way: man-made earthquakes. For years, residents in places like Texas and Oklahoma, places that aren't exactly known for intense seismic activity, suddenly started experiencing hundreds of unexpected earthquakes every year. Local monitoring stations that were totally quiet before were suddenly lighting up constantly. The culprit? Well, it wasn't just the extraction of the oil itself, but what happened right afterward. Here's the exact chain reaction. To get rid of the millions of liters of dirty, toxic wastewater brought to the surface, companies pump it straight back deep underground at incredibly high pressures. This fluid inevitably finds its way into old, deeply buried tectonic faults and the cracks between massive rock plates. At those extreme depths, this water acts exactly like mechanical grease. The friction between those giant, compressed rock plates suddenly drops, they lose their grip, and massive rocks violently slip past one another. The result? Immense pressure waves that literally shatter the rock and shake the Earth's surface. Looking at those collapsing seabeds and the induced earthquakes, you might be thinking we're on the verge of uncontrollable disaster here, which brings us to a really vital question. So how do we control this underground chaos without completely destroying the surface we live on? I mean, we can't just keep blindly blasting holes and pumping blind pressure into the Earth's crust. The answer actually lies in a massive shift from sheer brute force to high-tech precision. Enter the digital revolution of resource extraction. Today, engineers aren't just blindly forcing fluids, they are carefully massaging the Earth. Think of it like using supercomputers to gently squeeze an underground toothpaste tube. They're forcing the remaining fuel exactly where they want it to go, actively managing the immense natural forces rather than just stubbornly fighting them. But to do this, they actually need to see into the pitch black of the Earth's crust. So they spread thousands of sensitive sensors across the surface and send powerful acoustic sound waves, essentially small controlled vibrations, up to 5 kilometers deep into the ground. It works exactly like a submarine sonar. The sensors capture the echoing signals bouncing back from the different rock layers. Then supercomputers take all this data and build an exact, high-resolution 3D digital map of the entire underground reservoir. Engineers can look at a screen and literally see every crack, every layer, and exactly where those remaining oil pockets are hiding. Armed with this perfect map, they execute what is genuinely one of the greatest engineering miracles of our modern age: horizontal drilling. Now, in the past, you could really only drill straight down, but now, a massive, heavy steel drill pipe goes kilometers straight down, and then, controlled by an operator all the way up on the surface, it delicately bends a full 90 degrees deep inside the Earth's crust. It turns completely horizontal, sweeping across huge underground areas, basically vacuuming up specific oil pockets without having to destroy vast stretches of the surface above with thousands of separate wells. And this brilliantly illustrates how the pipes themselves have essentially become smart robots operating miles underground. Advanced navigation tracks the drill head's exact location in real time.
Electronic sensors measure the pressure, temperature, and fluid composition every single second. If a sensor detects that a section of the rock is starting to pump mostly useless water, a computer on the surface sends a signal down, and an automated mechanical valve plugs that specific hole in just 1 second, leaving only the pure oil channels wide open. The surface operator is essentially sitting in front of a control panel, playing a massively complex video game, using real, physical forces kilometers beneath their feet. When you step back and look at this entire process, it kind of changes everything you thought you knew. Modern extraction is this high-wire act of digital science holding back total geological devastation. It's not just a mechanical job of digging holes anymore. It's an incredibly complex dance of physics, chemistry, and computer science. Literally every drop of petrol in your tank is the direct result of hundreds of intelligent programs expertly balancing the immense crushing forces of nature. Which brings us to our final thought for this explainer. The next time you're standing at the petrol station, holding the pump and filling up your car, are you just going to see a mundane liquid fuel? Or will you picture the 300-degree heat, the crushing weight of 10 million train cars, the bent steel pipes miles beneath the earth, and the absolute technological triumph required to pull that black gold from the earth's crushing depths? Think about it. Thanks for exploring with us, and I'll catch you in the next one.